In this problem, we're going to look at a set of data on SAT scores from a high school. What we're told is that the SAT scores at this high school are normally distributed with a mean of 500 and a standard deviation of 100. And we're asked to find the probability that if I chose a student at random, that their SAT score would be in a few different ranges. Since our SAT scores are normally distributed, a good way to draw a picture of this distribution is to use a normal curve. A normal curve is drawn by an equation or a function, but we're not really concerned about the function that was used to create it. We're more concerned about the picture and how this function lies over the scale of SAT scores. A normal curve has its highest point over the mean, which in this case would be 500. And then the curve symmetrically fades away as I move away from the mean. We can see here on the tick marks on our picture that each mark is one standard deviation away from the one before it, with a standard deviation being 100 points in this case. What we're asked to do in part A is find the probability that a student scores higher than a 675 on the SAT. That probability is represented by these symbols here. To get that probability, it is represented with the area underneath the normal curve in this shaded region right here. Since I'm looking for the probability x is greater than 675, that would be to the right on the x scale, so the probability is represented by the area under the curve to the right of that value. Now the way I get the area under a normal curve is I use something called the standard normal curve, which is a similar scale, but it converts x values into z values. A z value is essentially how many standard deviations away from the mean an x value is. So we can see with an SAT score of 500, that is the mean, that has a z value of 0. And an SAT score of 600 would have a z value of 1. The score I'm concerned with, 675, has a z value of 1.75. And I got that number by converting it using this formula right here. I took my SAT score and subtracted the mean to see how far away it was from the mean, and then I divided it by what a standard deviation is. In this problem it's 100. And it tells me that an SAT score of 675 is 1.75 standard deviations above the mean. To get the probability that a student scores more than 675 on the SAT, it's equivalent to any normally distributed variable being more than 1.75 standard deviations above the mean. That's what this syntax right here means. That probability is represented by the area under the standard normal curve to the right of z is 1.75. Now to find this area, I can use a table. I'm going to use my normal table, which is uploaded on Moodle, and you can also find it in your textbook. My normal table lists areas to the right of z values. To find this area, I'm going to use a table, the normal table. You can find it in your textbook or upload it onto Moodle. Now my normal table lists areas to the left of particular z values. So if I use this table to look up a z value, I can find the area to the left, represented by this shaded region right here. For example, if I wanted to look up a z value of negative 2.53, what I would do is go down the left column of my table and look up the ones digit and the tenths digit, in this case negative 2.5, and then go across the top of my table and look up the hundredth digit, which would be 0.03. Matching up negative 2.53, that row in that column, leads me to an area of 0.0057. That would be the area underneath the normal curve to the left of z is negative 2.53. In our problem, we're actually looking for the area to the right of a z-value. Since my table only lists areas to the left, what I'm going to do is I'm going to look up z as 1.75, but the area I look up will be this big blank region in here. So when I look up this area, I'm going to subtract it from 1 to get the shaded area that I desire. Going back to my table, I want to make sure that I'm looking up positive z 1.75. So I'm going to flip to the page that has positive z values and go down the left column and look up 1.7, and across the top row I'm going to look up the hundredth digit of 5 to give me 1.75. So going down this column and matching it up with the row of 1.7, I see here that I have an area of 0.9599. That's the big blank area to the left of z is 1.75. Or in other words, it's the probability that z would be less than 1.75. This probability I would want to subtract from 1. 1 is the area under the entire normal curve. Subtracting that from 1 gives me 0.0401, which is the shaded area I desire. It's the probability that any normally distributed variable would be more than 1.75 standard deviations above the mean, which relates in our problem to an SAT score of 675. Moving down to part B, I'm asked to find the probability that a student scores less than 450 on the SAT. The probability that x is less than 450 would be to the left in this case, so I'm looking for the area under the normal curve to the left of x is 450. To find that area, I'm going to use the standard normal curve and find the area to the left of z is negative 0.5. I got that z value by converting it. 450 minus 500 divided by 100 gives me negative 0.5 standard deviations away from the mean. It's a little bit easier to find this area because my table lists areas to the left of z values. So I can just go to my table, look up this z value, and the area will be right on the table, and that's going to be my answer. Heading back to my normal table, I want to go to the page that has negative z values down the left side. I'm looking up negative 0.50. So I go to negative 0.5 in the leftmost column. And then the hundredth digit is a 0. So it's going to be this first column that I want to match up. So looking up z is negative 0.50 gives me an area of 0.3085. That's the area I desire, and that's the probability that a student scores less than 450 on the SAT. In part C, I'm asked to find the probability that a student scores between 450 and 675. That would be this middle region right here. To get that area, I'm going to use the standard normal curve and find the area between z is negative 0.5 and z is 1.75. We already did those conversions from x values to z values in part A and B. It's a little bit tricky to find the area between two z values when my table only lists areas to the left of z-values. So what I'm going to do is take the larger z-value, 1.75, and find the area to the left of that z-value. That's actually something we did in part A. It was 0.9599. But what we have to remember is that this number is the area from z is 1.75 all the way to the left. So it includes this shaded area, but also this blank space, which I do not want to include. So what I'm going to do is find the area of this blank space and subtract it from 0.9599. The area in this blank space is the area to the left of z is negative 0.5. That's actually something we found in part B of this problem. So that area 0.3085 is this blank space right here, and subtracting it from 0.9599 will give me the area I desire, 0.6514, which is the probability that a student scores between 450 and 675.